The Fundamental Theorem of Calculus. Here we have the integral from 1 to 2 of 4x minus 1 over x squared dx. We're going to apply the Fundamental Theorem of Calculus to this definite integral, meaning we need to find the antiderivative of 4x minus 1 over x squared to start. So let's remember that we need to rewrite 1 over x squared as x to the negative 2 before finding the antiderivative. So the antiderivative of 4x is going to be 4x squared over 2. And then the antiderivative of x to the negative 2 will be x to the negative 1 over negative 1. Now we're not going to put a plus c because this is not an indefinite integral, this is a definite integral. So we're going to evaluate this on the interval from 1 to 2. I am just going to simplify my antiderivative a little bit to be 2x squared plus 1 over x evaluated from 1 to 2. Now what we do is start by substituting the upper limit of integration into each x. So that would leave us with 2 times 2 squared plus 1 over 2 minus, now we plug the lower limit of integration into each x. So since there's two terms here, we want to make sure and use parentheses. So we have 2 times 1 squared plus 1 over 1. So now let's bring our work up here to simplify. 2 squared is 4, 4 times 2 is 8, so I have 8 plus 1/2 minus, and then in parentheses here I have 1 squared is 1 times 2 is 2 plus 1 over 1, 2 plus 1 is 3, so minus 3. So we have 8 minus 3 is 5, so we have 5 plus 1/2, or in decimal form 5.5. So our answer to a definite integral here is going to be a numerical value, since this represents the signed area between 1 and 2 of the function 4x minus 1 over x squared. So it should not be a plus c. Here we have another definite integral, the integral from 0 to pi of sine of x over 2 dx. So we need the antiderivative of sine of x over 2. Let's remember that we can think about this as sine of 1/2 x. So the antiderivative here is going to be negative 2 cosine of 1/2 x. So the antiderivative of sine is negative cosine. The 2 is coming from the reciprocal of 1/2. And this is evaluated from 0 to pi. So first we'll substitute in the upper limit of integration, pi. So we have negative 2 cosine of pi over 2 minus negative 2 cosine of 1/2 times 0, which is 0. So now cosine of pi over 2, this is 0. So I have negative 2 times 0 plus 2. So minus a negative gives me positive, and cosine of 0 is 1. So we end up with just positive 2 as our numerical answer. Now we have the integral from 0 to 3 of e to the 3x minus x dx. Let's find the antiderivative of e to the 3x minus x. Here we're going to get a 1/3 e to the 3x minus x squared over 2. And then this is evaluated from 0 to 3. So we'll substitute our 3 into each x first. So we'll have 1/3 e to the 3 times 3 minus 3 squared over 2 minus, and now we'll substitute in 0 into each x. And we need to have parentheses here because there's two terms. So we're going to have 1/3 e to the 0 minus 0 squared over 2. So let's simplify this a bit. We have 1/3 e to the 9th minus 9 over 2. minus over here, 0 squared over 2 is 0, but e to the 0 is 1. So we want to make sure and keep this 1/3 times 1. So it's going to be a minus 1/3 here. And then we can combine these constants if we create common denominators here. So we can have a common denominator of 6. So we'll have 1/3 e to the 9th. And then if we multiply the top and bottom by 3, we'll have 27 over 6. Multiply the top and bottom by 2, we'll have 2/6. So now we'll have 1/3 e to the 9th minus 29 over 6 as our numerical answer. Here we have the integral from 0 to 5 of 1 over the quantity 25 plus x squared dx. Now here we want to remember that 25 is 5 squared, and so the antiderivative here is going to involve arctangent. So it's going to be 1 over a, so 1 over 5, arctangent of x over a, so x over 5. Again, not plus c, because this is a definite integral, so we're evaluating this from 0 to 5. We start by plugging in 5 first, so we have 1/5 arctangent of 5 over 5 minus 1/5 arctangent of 0 over 5. And so now this is 1/5 arctangent of 1 minus 1/5 arctangent of 0. Well, arctangent of 0 is 0. So what do you plug into tangent to get out 0? You plug in 0. So this term is gone. But arctangent of 1, so what do I plug in within that restricted set of values into tangent to get out 1? Well, that's going to be the angle pi over 4. So arctangent of 1 is pi over 4, and it's multiplied by that 1/5 in front. So we end up with our numerical answer of pi over 20.